Hello and welcome to a video on covalent bonding. I'm going to be going through all of the simple molecule parts and there'll be another video on giant covalent compounds. Right, first of all, let's talk about forming and what covalent compounds are. So, first of all, it is a compound where electrons are shared between two non-metal molecules. So both, change the word molecules actually, I'll change it to non-metal atoms. So both atoms achieve a full outer shell, because everything is about stability. Getting to that full outer shell is the most important thing for them. They are getting there to become stable. So a good example we could talk about is H2H, hydrogen, H2. They are sharing an electron each. Now both of them have 2 in their outer shell, making them stable. Right, most of them, as I said, we're going to talk about small covalent compounds because most of them are small. So most covalent compounds are small. And by small, I mean 3, 4, 2, not many atoms involved. A giant one is something like diamond, where it has got millions upon millions of carbon atoms. Right, so that's just a quick intro on what they are. Now we're going to move on to how we draw them and how we represent them using models. So, just like with ionic compounds, you can do dot and cross diagrams, except for in this one, the shells are overlapping to show a shared bond, or sharing of electrons to form that covalent bond. So, dot and cross diagrams. Dot plus cross. We'll do hydrogen first as we talk about that, and I'll do another example. We'll do NH3 as well, ammonia. So hydrogen. How we'll draw these is we'll have a 1H. Now I'm going to use a different color for the other one so I can differentiate between the two. Now you make sure they are overlapping, because the overlap is where the bond is. Now hydrogen brings to the table 1 electron, and this hydrogen brings another one. So what you can see here is you've got 2, this one's got 2, this one's got 2. Therefore they are sharing electrons to both have 2 in their outer shell, making them stable. Right, now let's do a bit more of a complicated one. Let's do ammonia, NH3. So we've got 1 nitrogen, draw a circle around it, and we have 3 hydrogens. I need to make sure they're overlapping. Make sure they overlap. That is key in this, is to make sure. Now often in your exams they'll have drawn them for you to help you out, but if you are asked to draw it, do make sure they overlap. Just take your time with these and they will succeed. So this one I've done all the same color. I'm going to show you to make sure we differentiate between them. We're using dots on the hydrogen, so hydrogen equals a dot and nitrogen equals a cross. So nitrogen has 5 because nitrogen is in group 5, so it has 5 electrons in its outer shell. The group number tells us how many. So nitrogen in group 5 means it's got 5 in its outer shell. So it's going to give 1 to this hydrogen, 1 to this hydrogen, 1 to this hydrogen, and that means it's got 2 left over. So we've got 2 spare at the top. Now, hydrogen each have 1 in their outer shell, so this one donates 1 to the covalent bond, this one donates 1 to the covalent bond, and this one donates 1 to the covalent bond. Now what you'll see here is nitrogen will have 1, 2, 3, 4, 5, 6, 7, 8. 8 electrons in its outer shell. Nitrogen is stable. Hydrogen, this one has 2, stable. This one has 2, stable. This one has 2, stable. Hydrogen is now done. This is our dot and cross diagram for ammonia, NH3. And it shows us exactly where the bonds are forming. Another way we could represent this is by using a stick model. And that looks like this. So you can see, instead of using a dot and cross here, we could use lines. And these represent the bonds, but they do not show us the electrons. It doesn't show us how many electrons are in each one. Another thing is that this is 2D, and so is this. We live in a 3D world, and a big problem is that these are 2D. So to overcome that, we use what we call a ball and stick model. And the ball and stick model looks a bit like this. And it is to show a 3D structure. That's the hydrogen down to the larger nitrogen, another hydrogen, another hydrogen. Now this is meant to show a more 3D look to it. Admittedly, yes, I can't do that on here, but you'll often notice. So this one has 3D animations. We can see the angles and the shape, whereas these we can't see the angles and the shape, but we can see the electrons or we can see the bonds. Right, and now just to add a little bit more info to help you out, I'll keep that side of it. So, if you're a group 4 non-metal, such as carbon, you will form 4 bonds. And that's because 4 plus 4 will equal 8. If you're in group 5, such as nitrogen, you'll form 3 bonds. Again, 5 plus 3 equals 8. We know that because we've done it here. Group 6, such as oxygen, will form 2 bonds because it has 6 electrons in its outer shell plus 2 from the bonds, it will equal 8. Because the group number, as I've said before, group number is the number of electrons in the outer shell. And finally, group 7, such as chlorine, will have 1 bond because 7 electrons from the outer shell plus 1 from the bond equals 8. All of them add up to 8 because that is the stable magic number. Right, let's talk about a slightly more advanced one, double bonding. So I'm going to leave this down the side here so we can use it to help out talking about double bonds. So oxygen forms double bonds, and we're going to go into detail why. So both the oxygen atoms are from group 6. And that means they both have 6 in their outer shell. So they both want 2 to form that 8. So instead of them getting more oxygens in, they share 2 each. So we get 1, 2, 3, 4, 5, 6, 7, 8, 5, 6, 7, 8. And as you can see here, they've both got 8 around them, but in this time you've got a single bond here and a single bond here. And now we form what we call a double bond. 2 single bonds together equals a double bond, because we need to share more electrons in this middle bit, so they both have 8 in their outer shell. Now some, like N2 nitrogen, can form triple bonds, and that one in this example would look a bit like N. You got a dot across, a dot across, a dot across N. You've got 1, 2, 3, and that will be represented like that. So it's the same difference, it's just making sure we share enough, because they're both in group 5, 3 are needed to form that 8. Right, now let's talk a little bit about their properties and why we can understand bits about them using this information. So, a key property you do need to know is that they have low melting point and boiling point. Another one is cannot conduct electricity. So we'll start on this bottom one. They do not conduct electricity because they are not charged particles. And we need charged particles because it allows us to carry the electrical charge. So they are not charged particles. Unlike in ionic bonds where you have things such as Cl-, in this one we won't have Cl-, we'll just have Cl covalently bonded. Without that negative charge, you cannot conduct electricity. Now, let's go to the low melting and boiling point. Because they are small molecules, they have strong bonds together because they are covalent, strong covalent bonds. But the covalent bonds are not to do with the melting point and boiling point. Let's go back to the NH3. If we break this bond, we haven't got NH3 anymore, we haven't got ammonia, we've got NH2. That's something completely different. If we broke all of them, we'd have N plus H plus H plus H. It's not the same. It's not ammonia anymore. So it's not these things that we're breaking down. Because if we had to break them down, it would take a lot of energy because they are strong, and therefore they'd have a high melting point and low point and boiling point. Sorry. Now, in that case, we have to look at something else, and that's what we call intermolecular forces. Now, these are electrostatic forces in between molecules. These are weak. So, as they are between the molecules, so let's say we have NH3 again. Then we have another NH3 down here. And we have another one over here. What we find is that we form these intermolecular forces between different compounds. And there's a lot of them, but they are weak, so they're not very difficult to break. So it doesn't require a lot of energy for us to break them down. And that's why they have low melting point and boiling point, because you do not, let's spell that properly, you do not need a lot of thermal energy to break intermolecular forces. So this is why, because these are weak, it doesn't take a lot of the thermal energy to break them down. If we're trying to break these covalent bonds, it will take a lot more effort. And that is why when we go into the next video on giant covalent compounds, that's when we talk about diamonds made up of solely strong covalent bonds. They have a very high melting point, boiling point. But for simple small molecules, they have a low melting boiling point. And that's why a lot of them are gases or liquids at room temperature, such as water being a liquid, oxygen a gas, chlorine a gas, ammonia can be a gas unless you cool it a little bit, it can be a liquid. Exactly, there's none that are solid at room temperature. Right, thank you very much for watching.